Welcome to video 2 for unit 7. Like I said last video, this video is going to talk about torque and how that relates to angular acceleration. So we know in unit 2, well we know from unit 2 I should say, Newton's second law, it states that F, or some of the forces I really should say, is equal to the mass times the acceleration. Something we're all super familiar with by this point, I hope. You probably should be familiar with that at this point. Newton's second law, it plays such a big role in a lot of the other studies that we do in physics. I'm getting off topic here. So just like how a force will lead to an angular acceleration, we have. What am I saying? The force does not lead to an angular acceleration; it leads to a translational acceleration. But we do have a rotational analog for this. That being the sum of this little fancy symbol. It's probably a Greek letter of some sort that I don't know what it is. That's supposed to be the net torque. This net torque is equal to the rotational inertia, or sometimes called the moment of inertia, multiplied by the angular acceleration. So you might be asking, what is torque? Torque is just something applied to an object to get it to start spinning. For example, when you apply a force on a wheel, then depending on where you put it, it's gonna start spinning, right? If you put it at the very top and you yank to the side, then the wheel is gonna start spinning in that direction, right? If you're on the right edge and you start yank it down, then it's gonna spin in that direction, right? That force that you applied, it's called a torque because it's a force that you applied to get it to start spinning. Now, generally speaking, a torque, the formula for a torque is equal to the force applied multiplied by the radius or the distance from the pivot point multiplied by the sine of theta, where theta is equal to the angle between the force vector and the rotating body. To illustrate this, I'm going to draw a quick little diagram, right? Let's say I have this big long rod, and it's rotating at this very end, this big point at the right end, right? It's rotating about that end, so if I was to push it on this right end, it wouldn't move because that's the pivot point. If I applied a force in this direction with a magnitude F, then that angle would be theta. This distance would be r. So the torque applied would be equal to Rf times the sine of theta. Fairly straightforward, right? Just like angular acceleration, omega, and what did I just say? Just like angular displacement, angular velocity, and angular acceleration, if a torque causes an object to go counterclockwise, the torque is positive. If a torque causes an object to go clockwise, the torque is negative. There are some certain exceptions to that little rule, but it's few and far between. Those are rare circumstances, and you'll generally be able to realize, oh, that doesn't apply in this situation. Now you might be thinking, okay, well, what the heck is this little I variable that we have here? You said it was the rotational inertia? Yeah, it's the rotational inertia. The rotational inertia just describes how hard something is to rotate. Just like how a mass is based on how hard it is for something to accelerate, rotational inertia is how hard it is to get something to start spinning. Now, generally speaking, rotational inertia, I, is equal to the mass of the object times the radius of the object squared multiplied by a certain constant c. This c is a coefficient that depends on the shape. I don't remember some certain examples. Let me pull some up real quick. Let's see. Yeah, for a solid sphere, the coefficient is 2/5. For a hollow sphere, it's 2/3. So it very much depends on the shape. Don't try to spend your time memorizing this coefficient for every single shape because it's just not necessary. If you do need the coefficient or the formula, it will be given to you on the exam or whatever problem you're doing. Just generally know that if more mass is closer to the point of rotation, then the rotational inertia is going to be slower. If there's no, not slower, lower. If there's more mass further away from the rotation point, then what am I gonna say? Then the rotational inertia is going to be higher. Rotational inertia is also sometimes called moment of inertia, but two terms really are interchangeable. And as we know from last video, this little Greek letter over here, alpha, is of course angular acceleration. This is how torque and angular acceleration relate. Let's do a quick little practice problem with torque here. Let's say I have a little seesaw. That's the point. Like, the little triangle thing. That's the actual seesaw itself. We'll say I have a big block here. Let's say it has 10 kilograms. And we'll call this block 1. I'm so creative with my names. Let's say it is 0.3 meters away from this point of rotation. If I have a 15 kilogram block, where would I want to put this 15 kilogram block in order to maintain equilibrium? Okay, assuming that you've given this a shot. If we want to maintain equilibrium, then that means that the net torque is equal to 0. This means that torque 1 and torque 2, we'll say that the block we'll say the 15 kilogram block is block 2, and the torque it applies is torque 2. That means that this has to equal 0. I'm just going to draw an imaginary block here, like 15 kilograms. We'll say it's there, and we'll call that X, I guess. I don't know. Actually, no. We'll call it R2. Now, if we logically think about it, block 1, it's going to make the seesaw fall on that side. That would be a counterclockwise rotation, right? Because then it would fall down, and then if it would keep going, it would keep going in this direction, right? That's counterclockwise. So we can say that the torque from the first block is a positive torque because it's going counterclockwise, and counterclockwise is positive. That means R1 times F1 times the sine of theta. The torque applied by torque 2 is, on the other hand, negative, because this one is going to cause it to go this way, and it would keep going. That's a really bad spiral, but as you can see, that's clockwise, which in rotational kinematics is negative. So I'm going to denote that with a negative there. So then R2 F2 times the sine of theta is equal to 0. Now here, the only forces that are acting on the seesaw is going to be the force of gravity from both blocks. I have one pointing down there, one down that way, right? Both of these form a right angle with the seesaw because these forces of gravity will point straight down, and at equilibrium, the seesaw is going to be perfectly horizontal. So we have straight down, perfectly horizontal, that's going to be a perpendicular angle, right? 90 degrees. And the sine of 90 is equal to 1. That means that since sine of 90 is equal to 1, we can just basically cancel out because anything times 1 is just itself. Now that we have the sines cancel out, I'm just going to write this as R1F1 is equal to R2F2. And like I said, the only forces are going to be the forces of gravity. So I'm going to bring this over here. So R1M1G, that's the force of gravity for block 1, right? That is equal to R2 times M2G. That's the force of gravity of block 2. I'm going to rearrange this for R2, because that's the distance we're trying to find. This is R1M1G for M2G. These G's cancel out. So then R2 is equal to 0.3 meters times 10 kilograms divided by 15 kilograms. This comes out to be equal to 0.2 meters. So now we know that if we have a 15 kilogram block, we're going to place it 0.2 meters to the right of that pivot point. If we want to maintain equilibrium, of course. If we don't want to maintain equilibrium, then just put it literally anywhere else. Yeah, that's going to be it for this video. We went through torque. We've done a quick practice problem. I think that'll be good. Next video, we're going to be talking about angular momentum and angular impulse. Yep, we're going to Unit 4 again, but with angular stuff. I'll see you next video.